Hello, this video is for Stat 110, Section 6.1, and will cover pages 1 through 8. Okay, let's go ahead and get started then. So the notes for Section 6.1 are available at Stats class. Just grab a copy of those here. In Section 6.1, we got started with this, but I'll just do a quick review. What we were looking at is the amount of agreement between two doctors, two sets of measurements, a set of measurements that came from Dr. A and another set that came from Dr. B, and we're looking at whether or not these measurements tend to agree with each other. What we did then initially was to look at the differences between those two sets of measurements. And again, if those doctors are in agreement, we should have values that are close to 0. Here we can see that the first difference is 3, the next one is 8. We have a -2 here. That just means that Dr. A found less than Dr. B. I computed the differences here as Dr. A minus Dr. B. So that is important when you're interpreting the output to understand how the differences were computed. We talked about the fact that the average was about 2.75. So we can say Dr. A on average finds about 3 more of these palpal lymph nodes than Dr. B does. The standard deviation here is measuring the average distance to the middle. In this situation, we would like the standard deviation to be small as possible, because that means that these differences are more consistent. So the fact that the average is 2.75 and the standard deviation is 2.82 is telling me that these differences tend to be they tend not to be very consistent. They tend to deviate quite a bit from each other. And there are 32 differences there. This here is just a histogram of the results. We'll talk more about that later. What we're going to do here in section 6.2 is understand what's going to happen to the average, so this 2.75 number, not just for these data, but over repeated sampling. So how much is that value? How much can I expect that value to change if I were to get another sample? Okay, so that's what these pictures are about. I did ask the computer to take, looks like 5 different repeated samples here. The first time that I took a repeated sample, I got an average of 2.53, then 3.06, 1.91, etc. here. So those are going to vary a little bit, and we can see that in the next picture here. This is a picture of the average from each of those repeated samples. Okay, and one thing that I notice is that they stay away from 0. Now that's going to be an important quantity that I'm going to be testing here. I'm going to test my average against 0 because 0 means there's no difference between the two doctors. So if I go back up here and look at that difference calculation, if I have a value of 0 when I do this calculation, that means the two doctors agree. For example here, let me go ahead and get my little bit larger cursor for you. For example, right here, I have 7 from Dr. A and 7 from Dr. B. That's right at 0 there. Here's another one. 1 at Dr. A, 1 at, so that's 0. So when the two doctors are in agreement, I would want my differences to be around 0. In this picture, the picture over the repeated samples, it looks like I'm staying above 0. So that's what the test is going to do. Now, one situation with the test, when I do the test or conduct the test, I want to assume, or I do that under the situation of no difference. So what the test is going to do is look at how extreme is my average, which is 2.75, against the situation of no difference. So what we have to do with that distribution is just slide it down a little bit. We want to take this distribution, the one that I have up above, and just slide that so that it's centered right at 0. Now this data here exhibits no difference, because the average here, on average, I get a value of 0. So what I've done here is just shifted the data down by 2.75. Now I do my repeated sampling from this picture. And when we do that, I get lots of repeated outcomes, but now they're centered at 0 here. And this is what the computer is going to do as well. So when we do this test inside of our spreadsheet, it's going to center this distribution about 0 here for me. Let's talk a little bit about the p-value thing. the p-value quantity again. So remember, the idea of a p-value is to measure how extreme is my data. So let's go back up here and look at my data. My data had an average of 2.75. So how extreme is that value of 2.75 against a situation of no difference? So what we're going to do to calculate the p-value is compute how extreme 2.75 is against this picture of no difference. So the p-value is going to measure the percent of dots or percent of the distribution that's going to be above 2.75. And then also, if I'm doing a two-tailed test, I will need to worry about the lower end as well. So if I'm only doing a one-sided right test, I would only count the dots up here. If I was doing two-sided, I would do both sides. Okay, before going ahead with the test and the analysis in my spreadsheet, we do want to just mention one of the conditions for this test. Okay, or sometimes we call these assumptions. And that is that the distribution of my differences, so that's what I'm going to do my test on, the distribution of the differences, okay, should be kind of bell-shaped or normal-shaped. Now this doesn't look exactly bell-shaped, but it's pretty close. So that means that this test is probably going to be okay being applied to this data. So this is close to a bell curve. We don't have extreme skewness going on here. So my t-test that I'm going to run here in a moment inside my spreadsheet is going to be an okay test to run. If you have strong skewness here in this picture, you want to be careful about interpreting or using those p-values that I get from my spreadsheet. Because one of the conditions is that you have a symmetric bell-shaped distribution. In this situation, I'm okay. Okay, let's go ahead and do the test. Is there a significant difference in the average between these two doctors? Okay, so what we're going to do here is actually test our average. So that should probably be in the research question. So is there a statistically significant difference in the average between these two doctors? Again, if there is no difference, then that average should be at 0. Okay, so where was that picture again, or that, right? This indicates no difference. So when I take my research question and I turn it into something that I need to test, I'm going to test my data values against 0 here. I'm going to need this quantity right here when I do my test inside my spreadsheet. So we'll do that next. We're going to use the standard 5% error rate here. Okay, before I go into my spreadsheet, let's just talk a little bit about what I need to do. I need to compute the differences first. Okay, so this test is done on the differences. And then I need to specify what value do you want to test your data against. And again, I have 0 listed here. That value is coming from what I want to test here. Right there where my cursor is. Whatever value we have there is what I need to put that in my spreadsheet. Now that's normally going to be 0 because most of the time I just want to know whether or not I have a difference or whether or not there's an increase. So if a value is bigger than 0, then that would be an increase. When I'm doing this analysis inside my spreadsheet, it takes, again, 2 columns of data, the difference in the test value. The third quantity is the number of tails in the distribution. So this 2 right here is because I want to do a two-tailed test. If I am interested in just whether or not there's a difference, then that's going to be a two-tailed test. All right, let's go up to the Word version of this. In words, on average, differences exist. So I want to know whether or not there's a difference. This is a two-sided test. If I wanted to know whether or not Dr. A was bigger than Dr. B on average, then that would be a one-sided test. And I would need to change this 2 right here to a 1. Now the last quantity here, that last one, is because I am doing a paired t-test. So anytime I'm doing a test in section 6.1, this last quantity is going to need to be a 1. The value that is returned by my spreadsheet is indeed the p-value for that test. And this is what we would compare against 0.05. Okay, let me go over into a spreadsheet and just show you how to do that. So here in my spreadsheet, I have Dr. A, Dr. B. The first thing I want to do is compute that difference column. I can just do that with a formula. I can say B2 minus C2. Again, that's where that difference of 3 was. I can just do that for all of the values down, all the way down. If I wanted to get the average and such, what I could do to get the average is just use a pivot table. So if I highlight all the data here, go underneath Insert, Pivot Table. Under Values here, I can say I want to get the average for the difference here. So not the sum, but the average. So select difference for the values box and then just tell it what statistic you want to compute. And there's the 2.75 number. The standard deviation number, that's another option here. If I ask for the standard deviation, then that's the 2.82 number. The other one that we use a lot is just a count. How many do I have? 32. So I can specify the different statistic that I'm interested in right here. So that's how I got the average and the standard deviation, etc. Now let's go ahead and run our test. So let's come back over here. Again, what I need to do in order to run the test is to create a column of zeros here. So just double click, put 0 there, double click in that corner, and let's go all the way down. That should autofill that all the way down for me. Okay, let's go ahead and get the p-value then. So to get the p-value, what I need to do is equal TTest. The differences get highlighted first, comma, and then the value that you want to test against. I am doing a two-sided test, so I'm going to say comma 2, and then I'm doing a paired t-test, so I'm going to put a value 1 there. So again, the 2 is because I'm doing a two-sided test, which again comes from the H. I'm testing whether or not I have a difference here. So anytime I see difference there, or anytime I see not equal, that's going to be a two-sided test. Now this analysis is based on the differences. Okay, this analysis is based on the differences, so that is going to be the paired t-test. Hit enter, and the value that I get back out is again the p-value. 0.0000, it's very small. Very small indicates that I definitely have a difference here. So let's go back over here and pick up with where we left off in the notes. The p-value is, how many zeros are on there? 1, 2, 3, 4, 5 zeros. So report out the p-value, 0.12345. Okay, is 0.012345. Is that less than 0.05? Okay, yes indeed. So it's way less than that 0.05. So we have enough evidence for the research question. Let's go ahead and write a final conclusion then. It's been a little bit since we've done that. We have enough statistical evidence to say, okay, let's go back and get the research question. And the research question is asking about a significant difference between the two doctors. So we have enough statistical evidence to say that on average, there is a difference between Dr. A and Dr. B. And then we usually put that p-value at the end there. So p-value equal 1, 2, 3, 4, 5. There's the three components. We have enough statistical evidence because my p-value is less than 0.05. What are you testing? And then give the p-value there at the end. That conclusion there will get full credit. Okay, let's talk a little bit about the margin of error. So the margin of error, what we do with the margin of error is we go after the middle 95% of my data values. Oh, wait a minute. Don't say data values. What are these values? They are the averages over the repeated samples. So again, what we do to compute a confidence interval or margin of error is look at what's going to happen over the repeated samples. And then just give a range of where most of them are going to be at. Now, when we do the confidence interval and the margin of error stuff, we do not have to assume that there's no difference. So I'm going to get the confidence interval off of this distribution here. The one, again, that is centered at 2.75. So when I get the middle 95% of the values off of my confidence interval, it looks like I'm going to go down to about 1.75 and up to about 3.75. Now the math for this is provided here. All I need to do is start with the average difference, which is 2.75, and then I need to subtract 2 times the standard deviation divided by the square root of the count. Okay, so let's go ahead and grab a calculator and just do that math. I'll do one of those for you. So the math involved here is to take the square root of 32. I need that first, which is about 5.66, it looks like. So let's take 2.83, divide by 5.66, and I'm going to get about a half. And then I need to multiply that by 2. Multiply that by 2, and I get 1. So the math involved for the lower endpoint is going to be 2.75 minus 1.0. That's where I'm getting that number 1.75 up in that graph up there. For the upper endpoint, I just need to take 2.75 plus the value of 1, and that is the value of 3.75. Again, that's the upper endpoint up here. Teacher always picks the easy examples where the math is real easy. So my margin of error here is exactly 1. Now I'm using 2 here because if we go back to the outlier rule, back at the end of section 5, at the very end of section 5, I believe it was in section 5.3, in order to determine whether or not I had an outlier, I needed to go out 2 standard deviations. And that's exactly what we're doing here. Okay, so the lower endpoint's about 1.75, the upper endpoint's about 3.75. In between there, I'm going to get about 95% of my repeated averages, or my averages over repeated sampling. So that gives me a good idea of where my average is going to stay. That's what that interval is going to look like. Goes to 1.75 up to 3.75. Now, when I'm talking about the interpretation here, okay, so let's do a couple versions here. Let's do one that does not get full credit. Oops, sorry about that. Let's do one that does not get full credit. We are 95% certain that the data will be between 1.75 and 3.75. Okay, this is not good, or maybe I should say not perfect. What do we mean by the data? Okay, so let's try another attempt. We are 95% certain that the difference, or that, how about this? We are 95% certain that the average difference will be between 1.75 and 3.75. So now I'm talking about the average difference, and I'm giving you an idea that it's going to be in that range. But we can do a little bit better. So this is better, but not best, or whatever we want to say here. Okay, so what would be the best? We are 95% certain that Dr. A, that on average, Dr. A will find between 1.75 and 3.75 more than Dr. B. Okay, this is going to get full credit here. So this is our best version of these three. So I have the average, and then instead of just saying difference here, I'm actually telling you that Dr. A is finding more. Remember that a positive difference indicates that Dr. A is finding more. Right? If I go back up here and look at this a minute, a positive value, 4 minus 1, 3, that's a positive value. That means Dr. A is finding more. So when I'm looking at my 95% confidence interval, again, that goes from 1.75 to 3.75, this is staying above 0. So that means Dr. A is finding more than Dr. B. Well, when we're interpreting the confidence interval, tell me that. Okay, tell me that Dr. A is going to find more than Dr. B here. So if you just say the data is between these two numbers, you're not going to get very many points. If you say the average difference, that's definitely better, but tell me what the difference was. Okay, next let's go ahead and just look at a scatter plot of this data. So one thing that's true is that when I do this analysis, let's look at the spreadsheet here. When I do this analysis, I don't actually take into consideration what the differences were. What do you mean by that, Chris? When I do this analysis, I'm just looking at the difference column here. It's 3 and 8 and -2 and 3 all the way down. This analysis does not take into consideration what these values were. Now, if I look at them and remember, they were 4 and 1, right? So that's how I got the difference of 3. But the test itself, again, does not worry about what those values are. I mean, these values could have been 197. If they're 197, then being 3 off is not that much. But they weren't 197. They were 3 or 4 and 1. So being 3 off is actually a lot when I'm talking about numbers 4 and 1. So one shortcoming of this analysis that I just ran was that, again, it does not actually take those values into consideration. Let's look at the graphs that I made. When I create scatter plots for these things, or scatter graphs here, I do take into consideration these, the quantities, the values. I'm going to add a y equal x line to that plot because that's where y is Dr. B, x is Dr. A. The y equal x line is where they agree. So I can easily see here that 1, 2, 3 times they agree. I have 1, 2, 3, 4 times where Dr. B is larger. Pick on this one right here. Dr. A found 6, Dr. B found 9. So I have 1, 2, 3, 4 where Dr. B was larger. But a majority of them have Dr. A being larger. Most of the dots are below that y equal x line. So what does the y equal x line mean? Well, that's where they agree. How many fall exactly on the line? 3 of those. Most of those fall below the line, so that means Dr. A is finding more. We could add a trend line to that plot. And again, this is the line that goes through the middle of the data. And you can see that that trend line is below the y equal x line. So again, that's going to tell me that Dr. A finds more than Dr. B, because this trend tends to be below the y equal x line. All right, that does it through page 8, I believe. Let's see here. Yeah, I think this got, some of this got dropped down to page 9, but on the original notes, we will have another video picking up here with this second example. So one more time, the second video here, I will post another video where we will pick up with example 6.1.2. Okay, thank you for listening. Have a good night. Bye.